Hey calculus class! Today we're going to learn topic 31, Riemann sums and the definite integral. So, how would you calculate the most accurate value for the area under the curve? How does this relate to what we have already learned so far? So, as we've seen, with rectangles, with 4 rectangles, we get a fairly good approximation underneath the curve. But what if I was to increase the number of rectangles and keep increasing them until basically I get an infinite number of rectangles? In order to get the exact value of the area under the curve, we would want to calculate the area of an infinite number of rectangles. This is the same idea as a limit, in which we calculate the limit of the sums of the areas as the number of rectangles approaches infinity. So finding the area under a curve for any function. So step 1, you are going to divide or partition the interval from a to b into n equal pieces, subintervals, of with change of x equals b minus a over n. So it'll look something like this. So you have your area underneath the curve, and you're basically going to partition or divide the area up into n number of equal subintervals, where a, the beginning of your interval, equals x sub 0, and b, the end of your interval, equals x sub n. Step 2, you're going to write an equation for the area of any one given rectangle or trapezoid in any one given subinterval. Typically, the area in the ith subinterval, given between x sub I minus 1 to x sub I, is what we calculate. So, we are going to calculate the area for this given rectangle, basically the x sub I rectangle. So we're going to set it up for each of the 4, first starting with the right rectangular approximation method. So the base is the change of x, the height is f of x sub I, because I'm using the right rectangle, so I'm using the right endpoint of that interval. So then the area of the ith rectangle would be f of x sub I times change of x. For the left rectangular area approximation method, my base is still change of x, but this time my height is going to be the y value at the left x value of the interval. So f of x sub I minus 1. So the area of the ith rectangle for this one will be f of x sub I minus 1 times the change of x. For the midpoint, my base is change of x. So in order to do midpoint, we need the midpoint, or the middle x value between the two x values of my interval. So that means my midpoint value is the average of the two x values for the interval. So that means my height is going to be f of that midpoint x value. So the area of the ith rectangle here is f of half of the average of x sub I minus 1 and x sub I times the change of x. Now for trapezoids, this time my height for the trapezoid is the change of x. Base sub 1 is f of x sub I minus 1. Base sub 2 is f of x sub I. So that means that the area of the ith trapezoid is going to be change of x over 2 times f of x sub I minus 1 plus f of x sub I. Now, for step 3, you are now going to add up the area of all the rectangles or the trapezoids. So what do we use to represent addition of an infinite number of terms? Let's see how many of you guys remember this from Math and Al. Sigma notation. So, if we remember sigma notation, it's the crazy capital Greek E, okay? That's sigma. That means you're going to add them all up. So for the right endpoint, you're doing r sub n because you have nth number of rectangles. and you're going from I equals 1 to n. And then you're adding up the area of all of the right rectangles. For the left, same idea, but you're adding up all of the areas of the left rectangles. Midpoint, same idea, and trapezoid, same idea. These are what are called Riemann sums. Step 4. You are now going to take the limit as n approaches infinity to find the true area underneath the curve. No matter which method you used, they all should equal the same value. So that means that the area underneath the curve is equal to the limit as n approaches infinity of any one of these Riemann sums. So we're going to do an example of this, and we're going to use our good old example from topic 30, x squared between 1 and 3. And we already know that the correct answer is 8.6 repeating. But now we're actually going to get to that answer ourselves. So we are going to use the right rectangular endpoints because these are the easiest algebraically, okay? So that means we want to get the area of the right rectangular approximation by taking the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times the change of x. In order to do this, I need to get f of x sub I and the change of x. And how do I do that? So the change of x I know is going to be b minus a all over n. So that means I know my b is 3 and my a is 1. So that means my change of x is 2 over n. Now I can start out and find my x sub 0, which I know is the start of my interval, which is 1. Now to get x sub 1, the next x value, I know that my change of x is 2 over n. Since I'm starting at 1, to get the next x value, I would add my change of x to the previous x value. So that means x sub 1 is the previous x value plus my change of x, which in this case is 1 plus 2 over n. Now to get x sub 2, I do the same thing. Add the change of x to the previous x value. So when I do that, I get the previous x value plus 2 over n, and I can reduce that to 1 plus 4 over n. Then I'm going to do it again, x sub 3, to get 1 plus 6 over n. Basically, you keep doing this until you see a pattern. Then you can write x sub I. So I'm looking for a pattern between each of these x values. I know that they all have a 1 plus something over n. And if you notice, it's going to be my change of x times I, which means 1 plus 2 over in, where I is the subscript of the x. So since my change of x is 2 over n for the first one, notice that this is 1 plus 2 times 1 over n. This one is 1 plus 2 times 2 over n. This one is 1 plus 3 times 2 over n. Now since I have my x sub I to plug into f, I can now find f of my x sub I. Well, I know my function is x squared, so I'm going to plug my x sub I into x squared to get the following. Now we get to do some algebra. All right, so here's what we got so far. So for some algebra, you're going to want to expand out the 1 plus 2i over n squared to get the following. And you can do a little bit more simplifying. You can distribute that square through. And then you can also distribute this 2 over n through. So now we have this. Now, I'm not sure how many of you guys remember some of the sigma stuff, but in order to continue sigma, we have to separate each piece into their own sigma. Okay? So I'm just taking the sum of each of these three terms. And you're going to have to correct me in class, but I am assuming that you guys did do some practice with this last year in math analysis. So in order to continue from this point, you need to remember these lovely little formulas. Don't worry, I'm not going to ask you to memorize them, okay? So the first one, I want it to look something similar to one of these. So that means I can factor out these n's, because what I want, and if you notice in these properties, they all have i's, or a constant, okay? So the first one, I factored out a 2 over n, and I'm left with a 1. So that matches property A. In the second one, I factored out the 8 over n squared, so I'm left with an I. So that matches property C. And then the third one, I factored out an 8 over n cubed, which it leaves me with an I squared, which matches property D. So now what I'm going to do is transfer each one of them using that property. So that first one matches property A, which is just n. So I replace this whole sigma with an n. This next one matches property C. So I'm going to replace this whole sigma with the one that matches property C. So it's going to look like this. Then for the third one, I'm going to replace the sigma with the property D to get the following. Now, I'm going to go ahead and continue simplifying. So, basically my n's cancel here. I can do some more canceling, some distributing, etc. So, here the n's canceled. I'm left with 2. Here, the n and one of the bottom n's cancel. The 8 and the 2 also cancel. So I'm left with 4n times n plus 1. Here, the top n and one of the bottom n's cancel. The 8 and the 6 can be simplified as well to 4 and 3. And then I can distribute through n plus 1 times 2n plus 1 to get the following trinomial. I can go ahead and continue distributing. So I distributed the 4 over n to n, which gives me 4. The 4 over n to 1, which gives me 4 over n. And then I can distribute the 4 over n squared to each term here and on the bottom. Now I'm going to continue simplifying. So I know that 2 plus 4 gives me 6. And then I want to find a common denominator to create one fraction, because I'm eventually going to take my limit. So the common denominator is 3n squared. So I have to multiply each of these first two terms to get 3n squared. Combine like terms on the top. So now I have one fraction. Now I have my Riemann sum for this problem. And in order to get the actual area under the curve, I now have to take the limit of this Riemann sum as n approaches infinity. So that means that I am now going to have the limit as n approaches infinity of 26n squared plus 24n plus 4 all over 3n squared. I go ahead and plug in infinity, you should get infinity over infinity. So that tells me I can use L'Hopital. So when I L'Hopital both the top and the bottom, I get 52n plus 24 all over 6n. And when I plug in infinity again, I'm going to get another infinity over infinity. So I can L'Hopital again to get 52 over 6. And 52 over 6 is just a constant, and I can reduce that to 26 over 3, which, if I was to divide that, would give me 8.6 repeating. Just so you know, the AP test will never ask you to do this, but your college professor will expect that you have seen this. Okay? And I will not have you do this on a test either. Okay? All right, so now we have our formal definition of a Riemann sum. The definition states, if f is a continuous function defined for a is less than or equal to x, and x is less than or equal to b, we divide the interval from a to b into n subintervals of equal width, which is the change of x, equal to b minus a over n. We let a equal x sub 0, and then we have x sub 1, x sub 2, x sub 3, and so on till we get to x sub n, which equals b. Be the endpoints of these subintervals, and we let x sub 1 star, and so on, be any sample points in these subintervals, so that x sub I with the star lies in the ith subinterval, xi minus 1 to x sub I. Then the Riemann sum is the sum as I equals to 1 to n of f of x sub I with an asterisk times the change of x. So this is just a diagram to see what it looks like. It's pretty much the exact same thing, but the little asterisks just mean as some arbitrary x value. So the definite integral. The definite integral is the area under some function f. In other words, the definite integral is the limit of the Riemann sum as n approaches infinity. And this is what it looks like. So we say the integral from a to b of f of x dx equals the limit as n approaches infinity of the sum from 1 to n of f of x sub I times the change of x. So the notation for the definite integral. So this is my general notation for a definite integral. This lovely elongated S or curlicue is called the integral sign. The A is your lower limit of integration. B is your upper limit of integration. The f of x, that is the function, and we call that the integrand. The dx is the x is the variable of integration. So it's also kind of considered kind of like your change of x, because your change of x gets really, really small as you're going to an infinite number of rectangles. This whole thing is called the integral of f from a to b. And this equals some number. And that number is when you find the value of the integral, you have evaluated the integral, and this value is the area under the curve. All right, so we're going to use an AP style question for an example. The rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. The table below shows the rate as measured every 3 hours for a 24-hour period. Use a midpoint Riemann sum with 4 subdivisions of equal length to approximate the value of the integral from 0 to 24 of r of t dt. Using correct units, explain the meaning of your answer in terms of water flow. So we want to split this up into 4 subintervals. So that means my change in time, or the change of x, is going to be b minus a, so 24 minus 0, over n, which I know is 4 because they told me that's how many subintervals I have. So my change of t is 6. Since I am using midpoint, what that means is that I know that my rectangles are going to be every 6 hours. So that means I have one rectangle here. I have one rectangle here, another one here, and another one here. Now, since I want the midpoint of each of these x values, then that means since I want the midpoint of each of these x values, that means I'm going to use 3, 9, 15, and 21. So when I set up the Riemann sum for this, that means I'm going to use these four values for the rate of water flow as the heights of my rectangles. And I know my change in x, or the width of the rectangles, is 6. So that means I have 6 times 10.4 plus 11.2 plus 11.3 plus 10.2, which gives me approximately 258.6 gallons. Notice I included units. The problem did tell me to include units. Now I still have to explain this meaning in terms of water flow. So what this means is after 24 hours, approximately 258.6 gallons of water has flown out of the pipe.